Good morning, everyone. Thank you for being here today. I'm Xin Liu. I will talk about my work, VMscatter, versatile MIMO Backscatter. This is joint work with my colleagues, Zicheng, Wang, Yao, and my advisor, Ting. Firstly, I briefly introduce the Backscatter and MIMO. In the last few years, Backscatter has been proposed to transmit data on ambient signals, such as LTE, Bluetooth, Wi-Fi, LoRa, FM radio, and so on. By using switch, the Backscatter device can consume very little energy and also enable lots of IoT applications, such as device tracking, smart homes, and smart health. On the other hand, the MIMO has been widely used and become an essential element in advanced wireless communications, such as Wi-Fi, LTE, and 5G. However, little work has been effectively integrated MIMO technique into the backscatter system. The only related work, MOXcatter, tries to reflect MIMO signals from the Wi-Fi MIMO sender. Although MOXcatter uses multiple antennas to transmit data, the data on different antennas are the same. In other words, MOXcatter doesn't use MIMO technique on the backscatter tag. Therefore, compared with traditional Wi-Fi backscatter system, such as FreeRider, MOXcatter has a higher bit rate and a lower throughput. Different from existing backscatter systems, our high-level goal is to design a versatile MIMO backscatter system. It leverages space-time coding and the spatial diversity features of MIMO to dramatically decrease bit error rate and increase throughput. With the MIMO technique on the backscatter tag, the backscatter communication can have a longer effective communication range, better robustness, and better reliability. And at the same time, VMscatter has a generic design. The generic design can help the backscatter to be extended to massive MIMO. We first discuss why VMscatter can leverage the diversity features of MIMO. Traditional MIMO systems leverage the complex models to create orthogonal symbols. The orthogonal symbols can provide the diversity gain, full diversity gain. However, it is hard for backscatter to create orthogonal symbols because backscatter cannot decode the incoming signals. As a result, even though the backscatter leverages the space-time coding to modulate the incoming signals, the reflected signals are not orthogonal. We discover if we meet two requirements, the MIMO backscatter model can have the same standard representation as the traditional MIMO systems. In other words, the MIMO backscatter system can also achieve full diversity gain as the traditional MIMO system. To save time, we skip the mathematical proof. You could refer to our paper. The two requirements are as follows. The first, the backscatter data is coded by using the space-time coding. Second, the only unknown value in the MIMO backscatter model is the backscatter data. To meet the requirements and achieve our design goal, we face the following challenges. The first challenge is how to implement space-time coding on the backscatter tag. Because the space-time coding has 4 states to code a data: positive, negative, positive conjugate, and negative conjugate. However, VMscatter only has 2 states, on and off. The second challenge is how to deal with the MIMO backscatter channels. The MIMO backscatter system is more complicated than the traditional MIMO system because we need to deal with the channel between the sender and the tag, and the channel between the tag and the receiver. The third challenge is how to achieve a generic design that supports N by K by N MIMO backscatter configuration. It is very important because based on this generic design, we can leverage various types of existing infrastructure. Here is the outline of our talk. First, let's focus on the modulation. The modulation has two modes, the reducing bit error rate mode and the improving throughput mode. We first describe the reducing bit error rate mode. We utilize allomotive code on the two antennas. For example, when we transmit data 0, 1, and slot T1, we transmit PCA from antenna 1 and PCB from antenna 2. And the time slot T2, we need to transmit a negative PCB conjugate and antenna 1. How do we realize the conjugate operation? We found that the backscatter data is a real number. The conjugate of the real number is itself. Therefore, we can still use the on and off to achieve the conjugate operation. For example, negative PCB equals to the negative E to the negative G pi. That also equals to 1. That means there is no phase change on antenna 1. And antenna 2, PCA conjugate equals to the E to the negative G0. This also equals to 1. Therefore, there is also no phase change on antenna 2. Here are other examples when the backscatter wants to transmit other data. In the improving throughput mode, we can observe that in each time slot, 2 data bits are transmitted on 2 antennas. This is different from relay work because relay work transmits the same data on different antennas. Therefore, compared with relay work, with 2 antennas, the throughput of VMscatter is doubled. To save time, we don't describe the coding method of the improving throughput mode. If you need more details, please refer to our paper. Next, let's talk about the demodulation. Demodulation can be divided into 3 stages. The first stage is to eliminate the pre-scatter channel. The second stage is to eliminate the post-scatter channel. The third stage is to extract the backscatter data. To eliminate the pre-scatter and post-scatter channels, we propose a special backscatter packet structure. The backscatter tag first transmits a 0 sequence during the ambient signal's long training field. It doesn't embed any backscatter data into the long training field. Therefore, the receiver can leverage its own channel estimation and equalization model to estimate the channel response. The estimation result will eliminate the pre-scatter channel. Next, the VMscatter tag transmits reference symbols to eliminate post-scatter channel. Because the pre-scatter channel has been eliminated and the reference symbols are predefined, the only unknown value in the MIMO channel model is the post-scatter channel. We can leverage the estimation result to eliminate the post-scatter channel. Finally, we transmit the backscatter data. We already have eliminated pre-scatter and post-scatter channels. The only unknown value in the MIMO channel model is the backscatter data. It can be decoded by using the maximum likelihood estimation. Here is an example. The blue circle in the IQ values are the ambient signals. The red circle is the expected signal shifted by pi by the backscatter. Figure B shows a received signal without equalization. We can observe that the circles are rotating. It is caused by channel interference. Figure C shows a signal passes through the equalization model of the receiver. In this stage, the pre-scatter channel is eliminated. Figure D shows a post-scatter channel is eliminated by the reference symbols. Now we can observe that most of circles are in the first quadrant. Then the phase change pi can be correctly demodulated by using the maximum likely estimation. Next, we talk about how to extend the MIMO backscatter configuration to n by k by n configuration. We already showed the coding matrix with 2 antennas. For the backscatter with 4 antennas, each element in the coding matrix can be represented by using the coding matrix with 2 antennas. If we iterate the above procedure, we can get the coding matrix with k antennas. Therefore, our design is generic. Finally, we show the evaluation result. We implement the MIMO OFDM sender on B210 USRP with 2 antennas. The receiver is implemented on 2 X310 USRPs with 4 antennas. We implemented VMscatter on a customized printed circuit board. It mainly has 3 components: a clock oscillator, a baseband processor, and an RF front. The RF front can connect 4 antennas. Therefore, there is a 2x4x4 MIMO backscatter configuration. We extensively evaluated under multiple real-world scenarios. They are shown in the slide. Since they have a similar trend, to save time, we mainly talk about the bit error rate, packet receptor ratio, and throughput under 2x4x4 configuration. The figure shows the bit error rate performance of VMscatter under reducing bit error rate mode. The x-axis is the distance between the tag and the receiver. The y-axis is the bit error rate. The red line is VMscatter, and the yellow line is MOXcatter. The figure shows the performance of VMscatter is much better than that of the MOXcatter. The bit error rate of VMscatter is reduced by a factor of 862 compared to the bit error rate of MOXcatter. We also evaluate the packet receptor ratio of VMscatter under different distance and packet length. We can observe that no matter for distance or for packet length, VMscatter shows more reliability than MOXcatter. We also show the throughput of VMscatter under improved throughput mode. With 4 antennas, the throughput of VMscatter is around 4 times as that of MOXcatter. Finally, our key contributions are as follows. Firstly, this is the first work that designed and implemented a versatile MOXcatter, a MIMO backscatter system. It leverages the diversity features of MIMO to dramatically decrease bit error rate and increase throughput on low-power backscatter tag. Secondly, to implement versatile MIMO backscatter, we address the special design challenges, such as how to implement space-time coding on the tag, and how to eliminate the impact of pre-scatter and post-scatter channels. Thirdly, our design is generic. It has a potential to be extended to massive MIMO. Finally, we build a hardware platform and extensively evaluate under multiple real-world scenarios. Evaluation results show that VMscatter can provide a faster and orders of magnitude more reliable communication than state-of-art backscatter system. Thank you for your time. Now I would like to take some questions.
Hi, this is Zicheng from UC San Diego.
Yeah.
I have a question that since the tag has to estimate the channel, there would be a huge computation complexity to get the channel taps. So can you comment on the complexity that the tag has to have in order to estimate those channels?
Do you mean what's the computation complexity?
In terms of how much extra time it takes to get the channel taps at the backscatter tag for its configuration.
Sorry, I can't follow you.
So my question is,
which part of the which is complexity?
Yeah, in terms of like the algorithm that you implement in the tag to change the weights, how much extra complexity do you add to the tag?
On the tag, right?
Right.
In fact, this coding method is a washer code. Washer, it's used it's always used in the CDMA. It's very simple. In fact, I realized that on the backscatter, it doesn't take too much computation complexity. Because the backscatter, we know the backscatter uses a switch to modulate the signal. It's 1, -1, 1, -1. It's if we study it deeply, we find that it's very similar to the washer code. You can refer to it. You can refer it in the CDMA technique.
Yes.
If you that's another discover. If we use multiple backscatters, and because the washer code can be used in multiple scenario, multiple device scenarios, so it can be help us to make the backscatter to use the multiple backscatter scenarios I'm not sure if my answer.
We can talk offline. Thank you very much.
Thank you.
Hi, Akshay from Carnegie Mellon.
Yeah.
So one of the baselines that you showed was actually on a 1x1x1 system. However, typical backscatter systems do not require these insanely large preambles and all the synchronization symbols that your system is making these backscatter tags transmit. So can you comment on comparison with typical 1x1 MIMO system, let's say LoRa backscatter and other systems, which should have less overheads and have much higher throughput than your system, despite having your system having 2 antennas?
Sorry, that's a long question.
Oh, sorry. So your 1x1x1 system, which the baseline which you chose to compare your MIMO system against, was it still sending all the synchronization equalization symbols?
Oh, do you mean the synchronization, right?
Yeah.
That's a great question.
Okay.
Do you mean I'm not sure. If your question is how to synchronize the backscatter with the senders if we use multiple backscatters or multiple senders, right?
Oh, no, I understood your approach to do that. What I mean is like typical 1x1x1 systems do not require all that. So the amount of overhead, was it considered in your comparison, which your system entails?
Sorry, I'm not sure.
Yeah,
maybe we can take it off.
maybe we can take it offline.
I think his question is like the synchronization overhead, the overhead that you have in your system. Was it considered for the 1x1x1 like baseline system?
Yeah. In fact, I'm not sure I should talk this because I read it in another paper. But I can tell you some of them, some of it. I don't recommend the synchronization on the backscatter. If you are familiar with the OFDM structure, you will find that the equalization model always exists in the OFDM receiver. Because when we use OFDM receiver to extract, to receive the backscatter signal, the equalization model will compensate the backscatter signal. So if you synchronize the backscatter signal and the sender, there are two phase change on the backscatter signal. One phase is caused by the channel. The other phase is caused by the backscatter. If your modulation speed of the backscatter is slower than the phase change by the channel, when you go through the equalization, the two phase change will disappear. So what do we do on the VMscatter? Backscatter, if we use the backscatter as a new kind of channel, backscatter, in fact, backscatter is another kind of channel. The difference between the real channel, the backscatter is fast changing. The real channel is flat fading. So what we do, we need to eliminate the stable flat fading channel and extract the fast changing channel. So if your modulation speed is lower, so what do we do on the backscatter? We need to make the backscatter modulation speed faster than the channel response.
Okay, I think we can take it offline.
Yeah.
Thank you. Let's thank the speaker.